EanTime runs independently from Windows. In this chapter we discuss the components of EanTime and how they are fitted inside and next to the Windows parts. EanTime for Windows is installed to run together with Windows on one PC. This is also called local EanTime or the local node. Windows and EanTime communicate via the Windows/EanTime interface. Because all real-time and Win32 threads share the same memory and CPU, the data exchange between the two environments can be very efficient, even allowing them to share the same memory blocks. Windows can be used on a single processor system, but it also supports multiprocessing when multiple cores are present, dual-core, quad-core, etc., hyper-threading. The EanTime kernel always runs on a single processor core. It can use that core exclusively with Windows using all remaining cores. This is called dedicated mode. Alternatively, the EanTime kernel shares one processor core with Windows and Windows use that core and all other cores. This is called shared mode. On a system with 4 or more cores, multiple EanTime kernels can be installed on separate cores. Windows then uses the remaining cores. An EanTime node running on a host in the EanTime distributed RTOS configuration, i.e. the host does not run a Windows node, is called dRTOS node. dRTOS nodes may be connected via Ethernet to a Windows host and utilize the real-time TCP/IP stack for the connection. In the case of systems that contain dRTOS nodes, the Windows host may or may not include an EanTime node. It is an optional feature. Certainly, the NTX element, RT interface extensions for Windows, must always be present on the Windows host. Further, it is not required that the Windows host always be present. That is, the host is allowed to go down and this will not stop a dRTOS node. Of course, if an EanTime node depends on some special service from the host, such as sharing information with a Windows application, then the EanTime node will be impacted by the host going down. A key difference between dRTOS nodes and EanTime nodes in an EanTime for Windows configuration is that the Windows host can disappear and reappear without requiring a restart of a dRTOS node, the real-time subsystem. Likewise, the dRTOS node utilizes dedicated hardware and does not need to ensure that sufficient CPU cycles are provided for running Windows. The real-time application can consume all CPU cycles. Windows can run on various types of hardware. For EanTime, we are only interested in Intel architecture-based PCs. Windows is structured in layers as indicated in the diagram. Applications use the Win32 API to communicate with the system. Within Windows there is no support for real-time requirements. The real-time kernel that is used in EanTime for all configurations, i.e. EanTime for Windows and EanTime distributed RTOS, is based on IRMX technology originally developed by Intel. IRMX has been working successfully in thousands of demanding real-time applications for over 3 decades. The EanTime version is the culmination of continuous improvement and upgrades. This way it is able to exploit advancements in processor technology today and into the future. A real-time application programming interface more similar to the Windows API was added. This API supports real-time processes that directly access the real-time kernel. For easier conversion of programs written originally for Windows, EanTime also supports an alternative API called iWin32. The EanTime and iWin32 APIs can be mixed. In order to let the real-time environment operate with Windows, additional software is necessary on the host. Context switching, management of the concurrent operation of both Windows and the real-time kernel is done by the Windows/EanTime interface encapsulating the operating systems. This interface is one of the innovations that differentiates EanTime from the competition, and it is the reason that EanTime is able to fully integrate with the Windows architecture. It is designed to minimize the impact that future revisions of Windows might have on this solution. NTX API, RT interface extensions for Win32 API. Windows applications can interact directly with EanTime applications using NTX calls. NTX allows access to in-time objects and facilitates both communication and synchronization between real-time processes and non-real-time processes. On a host system that does not include an in-time node, but that must communicate with in-time nodes on different hosts, only the NTX API is installed. In a real-time system, a stop caused by a software error is unacceptable. When Windows crashes, usually as a result of a condition in a Windows device driver, it shows a blue screen, often called BSOD, blue screen of death. There is some information on the screen and then the system halts. In-time changes this behavior and allows the in-time kernel to continue with all its real-time threads. Detecting a stop event in Windows. Windows 32-bit configurations up to, and including, Windows 7. The behavior is like this. Upon interception of a bug check, Windows freezes and the in-time kernel is notified. This method intercepts the bug check as soon as possible, but requires interfaces not available in newer versions of Windows. All Windows 64-bit configurations and Windows 8, and up, 32-bit configurations, the behavior is slightly different. Upon interception of a bug check, the BSOD is displayed and the memory dump, if configured, is written to disk, then Windows freezes and the in-time kernel is notified. In-time also can be configured to allow Windows to continue to complete the stop event and shut down when the system is in a stable state, taking advantage of still allowing Windows to create the crash report and automatically reset if desired. The occurrence of a Windows crash is reported via an event that real-time threads can wait for. It is then up to such a thread to decide on a continuation strategy. In a dRTOS node as well as in shared mode configuration where in-time share a node with Windows, system crashes are avoided by separating the address space of real-time processes from each other and using ring 3 wherever possible. In-time kernel code and data is running at ring 0. With the iWin32 API, an existing application can be recompiled without changes to run on in-time. Validation obviously still needed. In-time supports standard TCP/IP communication and a number of APIs. Beside the native in-time API, there also is an iWin32 API layer. iWin32 is a subset of Win32 that many programmers are familiar with. Win32 applications can communicate with in-time nodes using respective counterparts of the in-time APIs, global objects technology or network layers. Use the NTX functions to communicate with the in-time objects. Use the iWin32X API to access iWin32 handles. Use standard TCP/IP calls to access in-time and dRTOS nodes. Win32 applications can use in-time objects and iWin32 handles, independent of where they are located. This global objects technology makes it very easy to scale a set of Windows and in-time applications from a small configuration with a single PC to a large setup with many in-time nodes. In the case where the Windows node needs direct access to shared memory, the Windows and in-time nodes need to share the same host. The mapping of nodes to hosts in an in-time system can be done dynamically, normally defined during startup. In-time binaries run identical in in-time for Windows and in-time distributed RTOS configurations. DSM, Distributed System Manager, and Global Objects Technology, logically connect the individual nodes to behave as one system. Global Objects Technology is implemented in Windows via NTX and in in-time via GOBS. Every node runs DSM, the Distributed System Manager. DSM is a cooperative, distributed process that monitors the system at different granularity, node level, and process dependency level. Node level. DSM first publishes its node to the other nodes in the system and then actively keeps track of the health of all the other nodes. This functionality is provided, independent of any application running. Process dependency level. Processes that need each other to provide full functionality can publish logical dependencies with respective roles, called sponsor and dependent. DSM will monitor these processes and inform the sponsor or dependent in case of normal or abnormal termination. Inter-process communication, IPC, in EanTime is implemented with respective objects, e.g. semaphores, message queues, mailboxes. These objects are local to the node where they have been created. Global Objects technology allows to access the objects from any node in the system. Every node runs GOBS Manager to implement global objects. If a process wants to use an object on another node, GOBS Manager will create and maintain a reference object to that object. The reference object then can be used like a local object. GOBS Manager can support any object in nodes that share the same host. If the node is located on another host, GOBS Manager transparently will use GOBSNet to interact with the objects on that node. There only is one GOBSNet process on every host. As common for distributed systems, global objects must not assume that the object on the other node is always available. Thus GOBS Manager relies on DSM service to monitor the dependency of the reference object to the object on the other node. In a standard Windows configuration, the bulk of the OS runs in the confines of a single hardware task. EanTime uses multiple hardware tasks to provide maximum separation, including blue screen crash protection, between the two environments. As in Windows, the EanTime kernel uses rings to protect the real-time kernel from bugs in real-time applications. All of Windows is encapsulated into a worst priority real-time thread. This ensures that real-time threads can always have priority over all Windows threads. In a standard Windows configuration, the bulk of the OS runs in the confines of a single hardware task. EanTime uses multiple hardware tasks to provide maximum separation, including blue screen crash protection, between the two environments. As in Windows, the EanTime kernel uses rings to protect the real-time kernel from bugs in real-time applications. All of Windows is encapsulated into a worst priority real-time thread. This ensures that real-time threads can always have priority over all Windows threads.